Hi everyone, and welcome to this evening's Chemical and Physical Society talk. This talk is sponsored by our long-term sponsor, the SCI Group of London, and we're very thankful for them. And our president, Dr Alex, will now introduce our speaker.
Hi everyone, so tonight we've got Dr Alexander Archibald, who is a lecturer at the University of Cambridge, where he's been for over 11 years. He received his PhD in atmospheric chemistry from the University of Bristol, and he's also been a visiting scientist at the National Centre for Atmospheric Science in Colorado. His research involves the development and application of state-of-the-art chemistry climate models, and his talk tonight explores COVID-19 and its impact on the Earth's atmosphere. So I'll pass over to you, if that's okay.
Yeah, thank you very much. Can you all hear me okay? I guess a thumbs up or a affirmative.
Yeah, all good.
Excellent, brilliant. So I guess first, thank you to Chiara and everybody else on the organising committee for inviting me to give this talk. It's a shame that I can't meet you all in person and find out a bit more about what your interests are in chemistry, but still it's a real privilege to be able to talk to you tonight. And for those of you who are watching on catch up, whenever you're watching at your leisure. So I'm an atmospheric chemist, and maybe to begin with, just a brief sort of back history to my career. So I studied chemistry, I think F100, the BSc chemistry course at Bristol between 2003 and 2006. And during that time, I realized I was not very good at lab work. I didn't really understand inorganic chemistry, and mathematically, I wasn't quite up to the challenge of theoretical chemistry. So I thought potentially my days as a chemist were over. But then I discovered environmental chemistry, and I discovered the chemistry of the atmosphere. I was then really lucky to be able to pursue a PhD with Dudley Shellcross, who was my supervisor, and the Met Office. And you can see in my sort of affiliations and collection of affiliations anyway on this slide here, that the Met Office is a partner that's stayed with me my whole academic career. So they co-sponsored my PhD, and I've been working with them ever since, basically. So atmospheric chemistry, for those of you that haven't had the pleasure of studying it, really is just applied chemical kinetics. So you all will have studied chemical kinetics at some point in your careers. And as atmospheric chemists, we really just want to use that as a tool to try and understand what's going on in the atmosphere, why, and what can we do about it. And that question of what's going on and why, I think, is a really important question. And Ed Hawkins, who's one of my colleagues at the National Centre for Atmospheric Science, who's based at the University of Reading, has really pioneered the way that we can visualize what's going on. And for those of you that are old enough and will remember the Rio Olympics, you might remember the climate spirals. And this was a graph that Ed developed, or a graphic that Ed developed, which really, I think, gave a visually stunning perspective of climate change, showing that since the pre-industrial time to the present day, temperatures are rising, and really emphasizing the problem of climate change. Ed then developed this lovely rainbow graphic, which I'm showing here on the top slide. And this graphic shows the changes in surface temperature from 1850 to 2015, so nearly the present day. And what we can see is that whilst there was some cooling in the 1900s, in the early part of the 20th century, basically the last few decades have just seen a huge increase in surface temperature. And what I've done is to kind of copy this idea and plot the levels of ozone going back from 1850 to 2015. So ozone is a fairly unstable molecule. So unlike temperature, where we have records of the levels of temperature going back all the way to the 18th century, we don't really have real observations of ozone that we can rely on going back that far. We do have some measurements that Victorian scientists made, but they're pretty qualitative at best. So instead, if we want to understand how this molecule ozone has changed, we need to use computer models. And that's what the work of my group is focused on, developing models which represent both the chemistry and climate of our atmosphere. And with these models, what we can do is we can predict how climate changes, and our models do a very good job of that. Basically, our model is the Met Office climate model, and we can predict how ozone changes. And what you can see is that there's this really strong coupling. So as ozone starts to really increase in the atmosphere, then so does the surface temperature. And when I talk about ozone here, I'm going to talk about tropospheric ozone, or ozone in the lower part of the atmosphere. And if there's one thing that you should remember about ozone, it's good up high, bad nearby. And what we mean by that is that ozone in the stratosphere is what we want. We want a nice thick stratospheric layer of ozone because that protects our skin. But ozone at the ground level is toxic, is harmful to plants, and leads to something on the order of about 1 million deaths every year, premature deaths, that is. And also it's a greenhouse gas. It's probably the third most important greenhouse gas after CO2 and methane. So as you can see, models will feature a lot in this talk. One of the reasons that I like models is not only can we look to the past and try and understand the past, but we can also look to the future. And I think you'll find in the literature, there's a lot of work which is based on using models to make projections of what might happen in the future. But I want to begin with by just saying that predicting the future is hard. There are many scholars, including baseball stars, who've emphasized this. And I'm just going to reiterate that this is a tricky task. So some of these you might be familiar with, for those of you who know your faces of physical chemistry, but some of these you might not be familiar with. So this chap here on the left, I think, deserves particular attention. So his name is Dionysius Larder, who was a really well-respected engineer, but who predicted that as train travel would pick up and as trains would potentially be traveling through tunnels, that if they traveled through tunnels at high speeds, and by his calculations 30 miles an hour was a high speed, that people's eyeballs would be sucked out of their sockets by the vacuum that was created. Clearly, that was a prediction of the future which really was not very accurate. And as a chemistry climate modeler, what I want to do is not end up being like Dionysius Larder. And when we think about predicting the future, we also have to really think about how uncertain it is. And I think nothing brings that closer to home than the current COVID crisis. So the COVID-19 pandemic has had profound impacts on the atmosphere, and it continues to do so. There have been, I really couldn't even count the number of studies published in the last year on the potential impacts and changes occurring in the atmosphere as a result of COVID. And several of these have been incredibly important for the community of atmospheric and climate scientists. This paper here, published in Nature Climate Change in the summer last year, used activity data from sources like people's smartphones and other tracking devices and other types of information to just quantify the changes in activity in different sectors. And what we can see from these figures is the huge reduction in aviation, which has really been sustained, and the significant variations, but significant reduction in things like surface transport. The changes in aviation and the reduction of planes flying has actually had an important but kind of bizarre knock-on effect on reducing the accuracy of weather forecasts. And that's because the planes themselves make measurements of the atmospheric state, so temperature, pressure, wind speed, etc., which gets used to constrain weather forecast models and to improve their accuracy. And so the lack of that data has resulted in our weather forecasting systems being less skillful. But all of these changes have had, all of these changes in activity have had resultant effects on the gases that are produced as a byproduct of this activity. And I think one of the first things which was really striking to see was the changes in nitrogen dioxide column. So nitrogen dioxide absorbs very strongly, about 400 nanometers, and so can be seen based on satellite measurements orbiting the Earth. And what these figures here, which I stole from, I think, actually a BBC article, and they credited Copernicus and the European Space Agency, are the situation before COVID, so in March 2019, what the tropospheric NO2 columns look like. And what we mean by this is the total amount of NO2 integrated vertically from the surface of the Earth to the top of the troposphere, which is about 10 kilometers or so. And what you can see is that there are these regions where there are very high levels of NO2, and these tend to be associated with people. And then during the lockdown, as people stop moving around and stop traveling, then the NO2 levels drop off quite dramatically. So we can see in Paris, which underwent some very severe lockdowns, the NO2 column changes by orders of magnitude. Similarly, in the Po Valley in Italy, large changes in NO2. And closer to home, where I live in Cambridge, I was also able to look at some of the data measured by in situ or direct measurements. And so this graph here shows nitrogen dioxide data compared to a climatology or an average of 2017 to 2019. And what you can see is that when the first lockdown started, this vertical dashed grey line. Subsequent to that, then the levels of NO2 measured at this site in Cambridge remained much lower than the variability observed over the last few years. And interestingly, that was sort of sustained and has been sustained all the way through to the present day. So what my group does is try and understand exactly, how changes like these that we see for nitrogen dioxide might affect other gases present in the atmosphere and how those might affect climate. And the way that we do that is by using numerical models, which simulate all of the physics and chemistry that goes on in the atmosphere. The model that we develop and that we run is called the UKCA model, the UK Chemistry and Aerosol model. And you can think about this as a really complex simulator of atmospheric chemistry and weather. These figures here, this animation, just shows the simulation of carbon monoxide in the model, on a repeating loop over a period of about 4 days. And what you can see is that when run at very high resolution, So this is around about 20 kilometers. Each pixel is about 20 kilometers, and that's kind of the resolution of the model. Then, we produce features which look very realistic, I would suggest. So we can see big plumes of carbon monoxide over India and China, and from some fires here in Russia and Mongolia, and it also looks like some fires in Central Africa. And so what we want to do is use this model to try and understand how the recent changes associated with COVID have had an impact on climate. And this was a question that we talked about over a cup of tea in one of the group meetings that we had early on during the lockdown period. And a few of my PhD students then went off after we'd had this discussion and decided that they wanted to answer this. We posed the question of, well, what have been the climate impacts of the COVID lockdowns? They decided that they would quantify this by running a range of hypothetical simulations to assess the impacts of some idealized lockdown events. And so to do that, they developed this temporal profile, which basically simulates a hypothetical 3-month lockdown period. And what they did was look at the different sectors that we talked about earlier, so the transport sector, aircraft and industry, and made perturbations to the emissions of all of the gases and aerosols that come from these different sectors. They came up with these 4 storylines or scenarios, and you can see here in this table how these different storylines affect the global emissions of molecules like nitrogen monoxide, sulfur dioxide, black carbon, and organic carbon. And what's quite telling is that if we look at these scenarios, so we see that we have a control simulation, which just uses our business as usual emissions, so no reductions. And then if we look at this A1 scenario with a 25% reduction in industry, that results in about a 9% decrease in SO2 emissions. And then we can compare that with this scenario A4, where we make no reduction to industry. And then we have only a 1% decrease in SO2 emissions. So this emphasizes the fact that in terms of these different gases, they have very different sources. So aviation and ground transport tend to be very small sources of sulfur dioxide, whereas industry seems to be a much larger source of sulfur dioxide. And in fact, power generation would be an even larger one. And so we can compare these different scenarios to try and understand the effect of these different sectors. The first thing we did was to compare to that satellite data of the tropospheric NO2 column. And that's shown here. So the red bars with some uncertainties, those come from sampling different types of meteorology. They show us what our model predicts. And then the blue show 2 different satellite data sets of the change in the NO2 column. And you can see that by and large, our model slightly underpredicts the changes in the NO2 column, but does a reasonably good job. Particularly in Europe, it does a very good job, but in parts of East Asia, there are changes which occur that are recorded or captured by the satellite, which are not actually detected or not simulated as well in our model. But we think that might just be a resolution issue. So we then, obviously, as I said, we simulate all of the atmospheric chemistry that's going on, and we can simulate how that affects climate in our model too. And I mentioned tropospheric ozone at the beginning, and so what happens to tropospheric ozone is shown as a time series here on the left, where the different colors reflect these different scenarios. and we have here the percentage change in the tropospheric ozone burden. And so that's where we just sum up all of the ozone in the troposphere and look at how these different scenarios have resulted in differences in the ozone. And, you know, by and large, I was pretty underwhelmed when my students made this first plot. I was sort of convinced that there would be much larger perturbations than this. But nonetheless, I think this is actually quite an accurate representation of what went on. And we can kind of follow the story through by looking at the other species, chemical species in the atmosphere that are coupled to ozone or affect the ozone levels themselves. And the first of those is the hydroxyl radical, which is plotted here in this leftmost column on the right-hand side. And the hydroxyl radical you could think of as the atmosphere's primary detergent. It's like the fairy washing up liquid. It destroys all of the grease and grime and everything that we put into the atmosphere. And what we can see is that as a result of the COVID lockdowns, the levels of the hydroxyl radical are likely to have reduced. That's kind of consistent with all of our storylines. And we can see spatially where these reductions take place. And interestingly, what we can see in these plots here, which show altitude versus latitude, is that those changes in aviation really restricted to the Northern Hemisphere, which makes a lot of sense because that's where people live, and mean that the biggest changes, the biggest reductions in tropospheric ozone, hydroxyl radical, are happening in these regions of the upper troposphere. And what we can also do is look at the surface plots of the change in ozone. And what we see is, quite interestingly now, there are regions where ozone has actually increased in our model calculations. And these regions we can see here blown up in East Asia, in Europe, in parts of Southern Asia. These actually have also been observed in measurements and are associated with the fact that in these locations, often the levels of nitrogen dioxide and nitrogen monoxide are so high that those gases, NO and NO2, suppress ozone. And so by removing NO and NO2, the ozone levels in those regions actually increase. But globally, ozone decreases because of the global scale, and you could say on average, those molecules NO and NO2 drive the catalytic chemistry which produces ozone in the troposphere. So there's this really interesting, difference between different regions on the planet and how the COVID restrictions affected them. And what we can do then is start to tease apart the effects of the different sectors of emissions by comparing the results from those different storylines, those different scenarios that we run. So if we compare A1 to A2, we can isolate the effects of aircraft, and you can see that those emissions are having the biggest effect in the lower stratosphere and the upper troposphere. And this black line here, which looks like a Gaussian, that reflects the height of the troposphere. And the surface transport changes, you can see quite interestingly propagate all the way through the troposphere, and the industry changes are just very small for these two gases. We can also look at aerosols, and we can look at aerosol precursors. One of the most important, which I mentioned before, was sulfur dioxide. And we see that in our four scenarios, sulfur dioxide generally decreases because the emissions of sulfur dioxide decrease, apart from in this A4 scenario where we don't have any changes to industry. But those changes to sulfur dioxide emissions also result in changes in the rate of sulfur dioxide oxidation. And as we change the rate of the oxidation of sulfur dioxide, different processes can start to become competitive. Generally speaking, about a third of SO2 gets oxidized by the hydroxyl radical, a third gets deposited to surfaces, basically sticking to them, and the remainder can be dissolved into liquid water and turn into sulfate ions. That last process actually is very dependent on the pH of water, and so in very acidic conditions, actually, that can dominate compared to the other two processes. But the complex, nature of this system means that as we change the amount of OH, we change the sink for SO2 in the gas phase. As we change the amount of ozone, we change the chemistry that happens in the aqueous phase. And all of these couple to affect the growth of aerosols and the size of aerosols that we predict in our model. These quite complex plots on the right-hand side show us in panel D the percentage difference in the total aerosol mass. And it's split with these different colors into different types of aerosols. And we can think about aerosols in different modes. And the nucleation mode is really the smallest aerosols that are just forming as very sticky gases start to coalesce together and turn into aerosol droplets. And then we have these larger aerosols, which end up being as large as what we call coarse mode aerosols, which you might be more familiar with as sort of things like grains of sand and sea spray and things like this. The Aitken and the accumulation mode aerosols, as you can see, are quite severely affected by these changes in emissions associated with COVID. And what they do is they result in a change in the effective radius of our aerosols. And what we can see is we have a reduction in mass, but an increase in the effective radius of our aerosols. And that's important because the size of the aerosols has an impact on their ability to form cloud droplets, and also has a direct impact on the way in which they scatter light. And the impacts on forming cloud droplets we can see in this final plot F, which shows the difference in cloud droplet number concentration. And so what we can see is that there's been a decrease in cloud droplet numbers as a result of all of these complex emission changes and then the chemical changes that occur. I'm going to skip over that and get to the kind of the bottom line here, which is that through all these complex calculations that we've done, we're able to quantify the climatic effects of these changes in atmospheric composition. And I think what's important to note is that these are very minimal. So in fact, minimal climate impacts is the strapline or the title of our paper, which was published in Geophysical Research Letters last year. And the sort of the numbers here really represent almost impossible to measure changes to the climate system. So the values here are in milliwatts per meter squared. At the same time that we focused on these reactive gases and aerosols, a lot of people looked at carbon dioxide and also noted that carbon dioxide was unaffected directly by the COVID lockdowns. And the reason for that is slightly more subtle, and that's that these molecules that we've been dealing with here have very short lifetimes. So we could see the effect of changes in their sources in a few months. The lifetime of CO2 is probably on the order of 200 years on average. And so if we change the CO2 emissions, it takes a long time for the CO2 to respond. So you can think about it as being an oil supertanker steaming along. And just because you put the brakes on or you switch the engine off, that doesn't stop the supertanker, and instead it will keep moving forward. And so that's why we really need drastic action to remove carbon dioxide from the atmosphere and to reduce emissions of CO2 to zero as soon as feasible. We also looked at some of the aerosol forcings, and again, there's quite a bit of detail here, and I think for this talk, I'll skip over that. So that's kind of a tour de force on some of the impacts of COVID and climate that we've been looking at. I'd like to kind of wrap up all of this work by giving you a bit of my personal perspective on looking into the future. So what might we expect for the next 60 years? And I hope, you know, I sincerely hope that we don't see more pictures like this. And this is really what we want to avoid. We want to avoid these smogs. We want to avoid these extreme weather conditions. And we'll only do that by taking appropriate action. And I think this is where, in my mind at least, modeling is incredibly important, because modeling allows us to simulate different pathways to try and avoid these kinds of consequences. One of the most impressive modeling activities is run by the Met Office. I don't get paid to say that, but it's true. And in this project called UKCP18, they make predictions of how climate change will occur and what the impacts will be on the UK. And so what they do is run simulations at relatively high resolution globally, so 60 kilometer. So basically split the world into grid boxes, which are about 60 kilometers by 60 kilometers. So you can imagine how many grid boxes you need, many, and then start to scale things down to simulate things which are about 2 kilometer resolution over the UK. And then this then allows us to sort of read the information from here, the globe, to the regional, to the local, and understand the effects of climate change. And as part of this work, they look at different scenarios or storylines or predictions, whatever you want to call them, of what might happen. And the headline message doesn't change as you go from global resolution to very high resolution. That there are greater chances of warm and wetter winters and hotter, drier summers across the UK. So we can have a look at some of these estimates of what might happen. And the top two panels show us the summers being warmer, and that's what we can see here in the red colors. And so we have a probabilistic set of estimates. So that the mean, the most likely scenario would end up with summers being something like 4 degrees warmer, where we are in, well, where I am in Cambridge, and where you, well, I guess you might be all over the world actually. But if you were back at UCL, you know, you might be expecting very warm summers in the future by 2080. With the potential for extremely large changes. And similarly, the potential for extreme droughts as well. 60% reductions in summer rainfall is really quite devastating. But, you know, the flip side to that is that we might expect to see much warmer but wetter winters as well. So, so yeah, some really interesting science going on at the Met Office in making these predictions. And a lot of this data is actually openly available for people to explore and to understand what might happen. But these predictions, as I sort of said, were based on a series of storylines. But these storylines are kind of one narrative of the future. I think when we think about the future, there are lots of different things that might happen. And obviously we've kind of lived through, or we are living through Brexit at the moment, and that has all sorts of implications. And we're living through an energy transition, a net zero transition, and transportation transitions. And all of these have impacts on the atmosphere and atmospheric chemistry and climate. And if we think about transport for a second, one of my big bugbears is when I see vehicles which tout themselves as zero emissions vehicles. There is no such thing as a zero emission vehicle. There are zero tailpipe emissions, but all of these vehicles produce emissions. And some of the really toxic and really harmful emissions actually just come from the wear and tear of brakes, brake pads, and the metal components of the vehicles themselves. Now, electric vehicles potentially could be thought of as exacerbating emissions from these sectors, so what we call non-exhaust emissions. And that's because electric vehicles are about 25% heavier than their counterparts. We have a real problem with particulate matter, particularly in urban locations. I live very close to a busy road with a big bus lane, and the PM2 levels are illegally high. I've measured them. That's not going to get better with electric vehicles. And so we do need to think rationally about what problems we create by fixing other problems. There's been a huge amount of talk about the hydrogen economy, and this is not new. People have been talking about the hydrogen economy for the last 30 or 40 years. It's just now there's really, it seems like there's some finance behind this. Hydrogen could be thought of as acting a bit like carbon monoxide and converting the hydroxyl radical OH into the hydroperoxyl radical HO2 and water. And we can see this reaction here on the top line. And that can propagate the formation of tropospheric ozone, as modeling studies have shown before. You know, what we're assuming here is that some of the hydrogen which is being used to heat homes or to generate power leaks, and there are other ways that hydrogen might be stored, which include storing it as ammonia. Ammonia is probably much less likely to leak, and so we probably won't need to worry about that too much. But ammonia itself is a very important air pollutant and something which we really have struggled to get a hold of in the UK. Partly this is kind of due to agricultural practices, and you can see here the majority of ammonia really comes from the agricultural sector. But there is the potential for increased ammonia production and usage, and so there might be increases in ammonia from non-agricultural sectors in the future under a hydrogen economy. I'm going to skip over fracking. We did some work to look at the potential impacts of fracking on UK air quality and human health. As you could imagine, it kind of depends on exactly the nature of how much fracking might take place, but there is the potential that fracking comes back on the government's agenda of energy security, but I think that's very unlikely. In terms of net zero, one of the things that was quite interesting to watch was the almost arms race for organizations to tell you about how many trees they're going to plant. That's great. I'm a big lover of trees. I have trees in my garden, and I think they're wonderful things, but they do provide a source of carbon molecules into the atmosphere. So they produce all these wonderful volatile organic compounds like isoprene or 2-methyl-1,3-butadiene and alpha-pinene, which I couldn't tell you its IUPAC name, but it's this molecule here which gives Christmas its delicious smell, and pine trees their lovely fragrance. So again, they react in the atmosphere to form these peroxy radicals, which can convert NO into NO2 and so propagate ozone formation. And so there's a risk that if we rewild in a sense that leads to massive increases in VOCs, and we don't do anything to NOx emissions, then we may end up producing lots of harmful ozone. So I think rather than, oh, we shouldn't rewild, I think really the focus here should be to remove NOx from the atmosphere as quickly as possible. We also kind of need to be aware that there's some strong relationships between pollutants and climate itself. And so we are going through a whole bunch of consultations and policies to try and reduce air pollution. But we also need to bear in mind that we need to tackle with CO2 at the same time. These plots here just show how levels of ozone vary during different summer heat waves. So the 1976 heat wave, the 2003 and the 2018. And what we can see is that whilst the surface temperatures have actually started to increase during these heat waves, so the 2018 is when we recorded the highest temperatures, with Cambridge recording the highest ever temperature measurement in the UK. The levels of ozone have actually dropped off quite considerably. So in the late 70s, we saw several hundred parts per billion, whereas nowadays we're lucky during a high ozone event if we go above 100 parts per billion of ozone. So I think this is an idea about good news, but also this exponential or this quadratic relationship with temperature means we do need to bear in mind that if we don't do anything about air pollution, climate change itself will make the problem worse. And one of the reasons for that is that during these heat wave events, what can happen is that we can have emissions which come from sources which we don't really consider on average, such as wildfires. And again, there's some really worrying trends in the frequency of wildfires in the UK. And we can see here, these data show slightly old, but show the area of wildfires for last year, 2020, in red, compared to the average of the last sort of 10 years. You can see this huge increase in wildfires last year. And the last few summers have been really quite warm and hot, and we had a couple of dry winters, and really that might be something that we need to think about managing better in the future. I'm going to sort of wrap up now and again just say that predicting the future is hard, and it requires us to use models and scenarios, both of which are uncertain. And my final take home is that when people criticize models, I think often implicitly they really criticize the scenarios that the models are trying to simulate. And again, I have to take my hat off to Ed Hawkins, who came up with some brilliant ways to try and visualize the differences between the uncertainty in models themselves, the natural sort of atmospheric chemistry system, which is chaotic and dynamic, and the scenarios that we might use to predict what will happen in the future. And that's what these bar charts here on the right show us, is that uncertainty split into these different components. And we can compare those with the underlying data on the left, which basically show us for these different scenarios, these different storylines, which are called representative concentration pathways. And we go from RCP 8.5 to RCP 2.6. We see, ultimately the biggest difference comes from those scenarios. And that's what this visualization also shows us. But this visualization shows us as well that when we look at the global scale changes in tropospheric column ozone, actually our models aren't quite good enough for us to be able to predict what will happen in the next few decades. And so that's where I'm going to leave it. I think there's a huge amount of room at the bottom to make better models and to ultimately make better predictions. And I think there's some great resources, but also a couple of missed opportunities. So for example, this UK CP, which I talked about, really just focus on climate. And in the future, I'd really like to see more work which addresses the coupled nature of this whole problem. And I'll just finish on a picture of my group and the groups that I work with, as this kind of makes me feel good and nice to see, you know, people all together huddled up, and something I hope that we will be doing in the future. And yeah, just thank you very much for your attention. And if you have any questions, I'll be very happy to answer them.
Thanks, Dr. Archibald. That was a really brilliant talk, super interesting. I was pretty into those pictures of summer being hot. I know it's probably not the take-home message, but yeah, really interesting talk. I have opened up the chat, so if anybody wants to pop some questions in the chat, or if you want to raise your hand and speak one out, we've got one from Catalina, and it says, "Hi, amazing talk. What mechanism does the UKCA model use?"
Thank you, Catalina. I hope everyone's happy with the idea of a mechanism as just being a sort of network of chemical reactions, which we use to simulate all of the chemistry. So in UKCA, we use something called strat-trop, which is very, it's a bit like Ronsil, if you know what I mean. It does what it says on the tin. It simulates the chemistry of the stratosphere and the troposphere. It's a mechanism which I developed probably about 10 years ago. It's not incredibly interesting or exciting, but it does what we need it to do. So this is one of the challenges that we face, is that actually simulating chemistry is numerically very complicated or very expensive. And so as an atmospheric chemist, as a chemist, I want to put lots of chemistry in, but that slows the model down to a snail's pace. And so we have to try and find a balance. And so about 10 years ago, I developed this strat-trop scheme, which I think is a reasonable balance between the level of detail and the fidelity of the scheme. So being able to produce accurate predictions.
Thanks. Sophia, you've got your hand up. I think you can unmute yourself, can't you?
Yeah. Hiya.
Hiya.
Yeah, I was just going to ask about the models. What could we do, or what extra variables could we include to make a more complex model that is related, that is closer to reality than the ones that we have right now?
Cool. Excellent question. Thanks, Sophia. So if we think about modeling in this context, then often people think about process complexity, ensembles, which means running the models again and again and again lots of times to try and understand natural variability, and resolution. So those are kind of the three axes in which we could think about. The first one, resolution, is fairly, sort of straightforward. You just try and make the boxes in the model smaller and smaller and smaller so that they become more realistic. Obviously, atmospheric chemistry and physics isn't happening in boxes around us. But at the same sense, if we were to try and average a property over 100 kilometers, like temperature, that wouldn't be too bad. But if we tried to average something like the levels of nitrogen dioxide over 100 kilometers, we might end up with a very poor representation of reality. So making the models run at higher resolution is one way that we can make some improvements. The ensembles just means running more simulations. So all we need for that is just more supercomputer power or supercomputer time. So really, yeah, it's about the complexity of the processes. At the moment, this is where a lot of people are kind of tearing their hair out and thinking about using machine learning. So there's an open question about how machine learning could be used to provide a bit more insight into the problems than people have managed to get so far with pen and paper, or other ways of analyzing the data from these models. So I think that's one thing, and I think it's an exciting thing. I think there's a potential that machine learning could lead to some really important breakthroughs in this field. And then I guess the other thing is that we're driven by observations ultimately, and there are still huge bits of the world which we really know very little about. So the model is just really extrapolating over. And as a great example, the global south is a region which is really understudied. And a region particularly that I'm interested in is Africa. And that's a region where we have almost no measurements and very little information about what actually is occurring in terms of emissions and how they're changing. So I think actually observational studies, you might think it's strange, a modeler saying this, but observational studies which try and fill in those gaps would be really important, because they'll allow us to test our models and then work out whether we are missing key processes that are occurring in those regions. I hope that answered your question, Sophia.
Yeah, it did. Thank you.
We've got a comment in the chat from Catalina. It says, I think there's a workshop hosted by NCAR on atmospheric studies in Africa taking place early March. Yeah, I was quite interested in that. How come there is no minimal data? Is it just lack of research in that area, or?
Yeah, I guess there are multiple factors of why there's a lack of research there, some of them being sort of logistical, some of the locations are kind of difficult to get to. So there's also very little known about the middle of the Amazon, but there's more known about the middle of the Amazon than there is about the middle of Central African rainforests, for example. And yeah, there's huge sort of historical issues about why there's been little coordination with African partners and cooperation with African partners. And I think some of that's being addressed. So obviously, like the Newton Fund and the links between the foreign office and science offices in the UK sort of landscape means that there's a bigger drive to deliver science for society, and particularly developing nations. But yeah, there's plenty of appetite for it, and I have a project in Kenya at the moment where we're measuring methane from cows. So for those of you that know, sort of cattle farming is a huge thing in East Africa. And what we see in observations is that methane is increasing really rapidly in the atmosphere. And we want to know, well, how much of that is because of cow farming, how much of that is because of things like fracking, and how much of that is because of things like wetlands, which are increasing as well because of climate change. And the nice thing there is that the methane that's emitted from those different sources has different isotopic signatures. So we can have a look at the methane isotopes and then understand. And so actually working with people at Royal Holloway University, we went out and measured the methane being burped out by the cows in Kenya, which is quite fun.
Brilliant. Oh, just got, I think, one more question. So, from Tegan. Hi, Alex. Did you say that even though the mass of aerosols being released decreased, their effective radius increased? Why is this?
So one way of thinking about that, thanks, Tegan. That's a good question. If you yeah, so it's let me just get my head around this. Sorry, this is aerosols are a complex beast. So generally what you would think is that as you increase things like SO2, you might increase the number of potential sites to form cloud droplets. And so for a fixed amount of water vapor, so water will be condensing onto those aerosols, then you end up with lots of small particles. And then what happens if we decrease the number of nucleating sites, then the available amount of water stays the same. And so we then basically put more of those water onto the fewer aerosols that exist. So the the condensation droplets then become bigger. I hope that garbled explanation made a bit of sense. It did in my head. Yes. Yeah. Sorry, I'm just reading the...
Oh, yeah, that's good. That's brilliant. And you can probably see David Rowley's final question. That's, did methane levels change much in the lockdown simulation?
Yeah, so we didn't change methane at all because the lifetime of methane is about 10 years, and we were running simulations for just over a year. So we just decided to keep methane constant. In reality, I mean, one thing is, we can look at what's happened. And I think, I'm not sure about the final numbers, but I would imagine that because of the big crashes in the gas prices and hydrocarbon prices, there's probably a reduction in fracking and the production of natural gas because demand decreased. But I wouldn't be 100% sure on that. And that's the sort of the anthropogenic methane. The natural methane obviously ignored COVID and just did what it wanted to do. And so about 50% of the emissions of methane come from natural sources like these wetlands, which I talked about. Again, I've not looked at the methane measurements themselves, but they've been on an upwards trajectory, and again, that long lifetime means I'm sort of, I doubt we would have seen any impact over the last year on that upwards trajectory, and it might take a wee while for that to happen. I hope that answers your question, Dave, as well, and thank you for the kind comment.
Okay, great. Thanks, everybody. I think now I'm going to pass over to you, Miranda.
Yeah, thank you very much, everyone, for attending, and thank you very much to Dr. Archibald for the incredible talk.